Hi everyone, thanks for being here. My name is Paul. I was an undergrad at UCLA. I actually just graduated like a couple days ago, so not quite accurate anymore. But this work was done with my advisor, Professor Remy. He is the reason why this work was able to be completed and provided like so much helpful advice and guidance. So big thanks to Professor Remy. Not here today, but he is here with me in spirit. Great, so just as a very quick recap of what EGRAPHS are. EGRAPHS, you can kind of think of them as like a list of ground terms. So like for this really simple example, it's just like a times 2. And then you see that the sort of like the leaf e nodes are represented in yellow here. And then we have like a multiplication e node. And the classes are represented by the boxes that they reside in. The nice thing about EGRAPHS is that you can add more ground terms to the eGraph using rewrite rules. For example, in this case, we apply strength reduction. And a really cool neat feature of eGraphs is that it does term sharing and some other ways to reduce the size of the eGraph. In this case, we only have these 5 e nodes in order to represent these 2 ground terms. Now, a big problem with eGraphs is that with certain rewrite rules, especially associativity and commutativity, they tend to explode and grow in size very rapidly. So let's run through a quick example of that here. So let's start again with a ground term. This time it's a times 0. And then let's consider what happens when we apply 2 rewrite rules. The first one is just multiply by 0, and the second is associativity. So let me try a live demo. So this is just basically the eGraph that we had before, or rather the rewrite rules that we had before. And then we can see here that we start out with the same eGraph we had. It's just a times 0. And then if we are to apply these rewrite rules once, then we end up with this eGraph. And you'll notice here that only the multiply by 0 rewrite fires. And so we end up with an eGraph that represents the term 0, but also represents a times 0, but also represents a times 0. One nice feature about eGraphs, at least as they are implemented in EGG, which is the state-of-the-art library for representing eGraphs, and which is like will be the focus of my talk. A nice feature about eGraphs is that they can be self-referential. So in this case, we have like a bit of a cycle here. So it actually represents infinite terms, which is pretty cool. Now, as we continue running these rewrite rules, we see that the eGraph gets bigger, which is sort of what's to be expected. But you'll notice rather concerningly that as we continue applying these rewrite rules, the eGraph starts to get bigger much faster. And even just by the 4th iteration, we end up with this like big mess of spaghetti. And then if we get impatient and then try to run the iterations a few too many times, it's going to end up having way too many nodes. And then at least in this browser demo, it's not able to represent it. And so if we go and like take a look at the logs, and we go all the way down to the bottom, oh, it looks like it hasn't quite crashed yet. There we go. Now it's panicked. You'll see that our final eGraph size ended up being like multiple thousands of e nodes large. So that's not quite great for eGraphs, because the whole like sort of deal with eGraphs is that you want to be able to efficiently represent terms. Now, there's been a few proposals for addressing this problem. At least in EGG, there's a couple strategies that have been used. The first is scheduling. So you can control like when rewrites are applied to the eGraph. The default scheduler in EGG is known as backoff scheduler. It uses this like nice little exponential backoff algorithm that basically bans exploding rewrites, gives the other rewrites a chance to catch up. Another strategy that has been used in EGG, at the very least in its math.rs test suite, is pruning. So let's say we have this like eGraph here. You might recognize it from before. It has a root e class, and the root e class represents a whole bunch of different things, but also represents just the number 0. Now, the nice thing about this is that because it just represents the number 0, you can kind of like ignore all the multiplication e nodes and then just like get rid of them, and then you end up with an eGraph that just represents 0. So that's pruning. And in the course of this project, I discovered that there is a bunch of other strategies that people have used to address exploding eGraphs, which I think speaks to like how important the problem is. One of them is what's known as inverse transformations. The concept behind this is a bit abstract, so here's like a good example. So let's say that we have like a list of numbers, and then we like take their sum. This is actually equivalent to just taking the sum over the numbers like sorted. But you'll notice that the inside list, the 3, 2, 4, 1, 5, is not equivalent to range 1, 6. But because the sum operation is applied to them, the order is actually does not matter in this case. So with inverse transformations, you can basically consider the inside list as if it were sorted, and then you can apply rewrites to the eGraph with that knowledge. Another strategy is that you can reinitialize the eGraph with the best extracted term. So in the course of equality saturation, maybe once your eGraph gets really big for some arbitrary definition of big, you extract the best term from that eGraph, you throw away your eGraph, and then you start anew with a new eGraph. And then another technique that I've seen is what's known as guided equality saturation. This one's pretty interesting. Let's say like you want to write some kind of proof, and you know sort of the intermediate steps of that proof, but you want equality saturation to sort of fill in the gaps for you. With guided equality saturation, because you have these sort of intermediate terms, it allows you to complete equality saturation without running into the explosion problem too much. So with my talk, I want to introduce the idea of destructive rewrites. And with destructive rewrites, you want to take the existing rewrites that you have for your equality saturation, and then you want to automatically keep the eGraph small with those rewrite rules. So with my specific implementation, the way I did this is that for every single rewrite rule, we e-match on the left-hand side as usual, but instead of adding instances of the right-hand side, we actually remove instances of the right-hand side. There's a few other ways you could do this. Like one way you could do this, for example, is that you e-match on the right-hand side and then you remove the left-hand side, which might be more interesting. But just for this talk, we'll be focusing on this particular implementation. So let's run through a quick example. So again, pulling up the eGraph that we had before, let's say we wanted to undo the associativity rule. So we e-match, and then we figure out like what e-classes A, B, and C correspond to, and then and then we can pick, say, like that e-node on the left there that's boxed in pink as sort of like the top e-node that represents our left-hand side. And then when we take a look at like what e-node might represent the right-hand side, we might end up with this e-node. So with destructive rewrites, instead of sort of like adding that e-node to the eGraph, you would actually want to remove that e-node. So in this case, we remove the e-node, the multiplication e-node from the eGraph. One caveat is that the way that eGraphs are currently implemented in EGG, you don't really know like which rewrite an e-node came from. So even if that e-node was added by like a different rewrite, we're still going to remove it because it like matches the right-hand side. So that's a caveat to keep in mind, and I'll discuss that limitation a little bit more later. And once you remove your e-node, you want to be careful to clean up your unreachable e-classes. So like in this example, right, that multiplication e-node is the only pointer to the e-class that's boxed in pink. So we're going to want to make sure to clean that one up. There's a couple other things you need to be aware of with destructive rewrites. The main one is that besides clean up the unreachable e-classes, is that the eGraph must always contain at least one grounded e-class at the very end. Grounded basically just means that you can extract a term from it, so it still has to have like one of the leaf e-nodes at the very end. So let's take this eGraph right here. There's just 3 e-nodes in it, but we're interested in this plus e-node right here. And with this eGraph, if we try to remove the plus e-node, what we'll end up with is an eGraph that just has this function f pointing to itself. And so you'll end up sort of like with an infinite term. You'll end up with like f of f of f of f, and so on to infinity. So you can't actually extract anything out of this. So for the way I implemented this, for the way I implemented destructive rewrites, I just like simply do not permit removing that specific e-node. And then another e-node you can't remove is this one down here. Obviously, if you remove the last e-node of an e-class, you end up with an empty e-class, and you can't really extract from an empty e-class. So that's another rule that I implement, is that if an e-node is the last member of its e-class, you can't get rid of it. So those are the rules that we've for destructive rewrites. I tried implementing destructive rewrites in the math test suite for EGG and came up with some pretty promising results. So the baseline that we're comparing to has explanations disabled, first of all, because the way I implemented this doesn't work with the explanation system, and I'll cover that in a later slide. I also disabled pruning. So for the math test suite to complete on time in EGG, they use pruning in order to make sure that the eGraphs don't get too big. So just as a fair comparison, I got rid of both pruning and explanations. And so we can have this nice little log graph here with the destructive rewrites on the y-axis and then the baseline on the x-axis. And you'll see that with the destructive rewrites, it does end up being much faster for a few of the tests, and then up to like a couple orders of magnitude faster for one of them. And then just for fun, I also compared this like with pruning, but still with explanations disabled, just to give it a fair shot. And you end up with some mixed results. So it basically shows that like pruning and destructive rewrites, they basically end up like as a wash when you compare them, which is nice because it means that my approach is sort of like doing something similar to pruning, where it's able to remove enough e-nodes and e-classes from the e-graph to prevent the e-graph from getting too large and slowing down equality saturation. In terms of next steps, one thing that is the two things that are really important for destructive rewrites are thinking about like when you want to destroy rewrites and what rewrites you want to get rid of. The way I implemented it is that it's sort of based on the backoff scheduler system. If any of the rewrites get applied too many times, then I get rid of that rewrite, and then I wait an exponentially longer time until I get rid of it again. But for which rewrites we want to get rid of, I'm currently just undoing every single rewrite, and that ends up being quite aggressive. So you want to think about like maybe you want to automatically identify explosive rules. For example, associativity, commutativity, any kind of rule where the left-hand side and the right-hand side have like the same cost, so it doesn't actually end up like improving the e-graph in a greedy manner, are rules that you might want to consider. But it is like more complicated than that because with the example that I showed at the very beginning, it doesn't actually explode if you only have the associativity rewrite. It is the combination of the associativity rewrite and the multiplied by 0 rewrite that results in the graph exploding. So there is a bit of subtlety here that is important to keep in mind. Another thing I've been working on is trying out destructive rewrites in Herbie, which is a really cool research project that uses eGraphs for floating point optimization. So the accuracy of a floating point expression depends quite a bit on like how you arrange the operators in the expression. So rearranging them might result in much better floating point accuracy over like the range of possible floating point values. And Herbie uses eGraphs internally for that optimization. So this is pretty nice for benchmarking. So I've been working with this. It's currently so slower than if you like ran like Herbie just like normally. But it is nice that it like does finish on time. It's not like much slower. So I think like with a few more strategies, like for example, like only undoing certain rules, this approach might actually work. And lastly, as I was talking before, support for explanations is also still a work in progress. It turns out that the proof system in EGG is sort of like its own separate eGraph. And one really interesting thing about the eGraph that is used for the proof system, for the explanation system, is that it preserves history information. So for example, like which rewrite did an e-node originate from is a question that you can answer with the explanations eGraph. So since that gives more information, that might end up being useful for destructive rewrites in terms of like making sure they're like more targeted and making sure that you're not trying to like remove too many parts of the eGraph. Because as it stands, the EGG eGraph doesn't have enough information, so the removal of e-nodes and e-classes is a bit coarse-grained. But yeah, so that's what I have so far for destructive rewrites. That's my URL for the slides. My fork is up there. And then I'll be starting the PhD at Northwestern in the fall. So that's not my UCLA email because I won't have access to it anymore. That's my Northwestern email. So if you would like to contact me, please reach out. And I'd welcome any questions. Thank you for listening.
Thanks for the great talk. We have plenty of time for questions. Great.
Thanks, really interesting talk. So we have something that's sort of in the same domain in Cranelift's eGraphs, but almost a dual to this, which I find interesting. So if I understood right, your mechanism is basically that you match and then you say, okay, remove this specific thing. In Cranelift, we have this notion of a subsume operator where we say, here's the result of a rewrite, remove everything else. Which we found to be sort of a nicer, more local way of thinking about things, because sometimes we know that a rewrite really does get just the best possible answer. So like constant propagation, okay, if something goes to a constant, then we don't need any other expression. That's the best possible thing.
Yeah.
So I'm wondering if you've thought much about like when these different kinds of specifying destructiveness makes sense? Like what sorts of applications, and is one, are there use cases where they both make sense or something like that?
If I'm understanding correctly, that sounds kind of similar to like the pruning approach, where like because you know that an E-class represents a certain like constant value, you can kind of get rid of all the other E-nodes, and you're just left with the representative term. I think the way that destructive rewrites work can be adapted to work with that, because the way that pruning works in egg is that they kind of just toss out all the E-nodes, but it works for that because like it's like pretty straightforward. It's just like all the E-nodes you're trying to remove like are in the same E-class. If you're trying to do something more complicated, you would have to start thinking about like the groundedness rules, the groundedness rule that I was talking about. So I think like for those situations where you have like more complex removal of stuff from the eGraph, it might be useful. That was like sort of like the biggest issue that I ran into when I was doing destructive rewrites, is that because the eGraph like so extensively shares information, it is really hard to like touch one part of the eGraph and only touch that part of the eGraph and not have like the house of cards fall down on top of you. So.
It makes a lot of sense. Thank you.
Thank you for the nice talk. The destructive rewrites was not as fast as like Herbie normally running. But what about accuracy? Like, was it finding the same answers?
That's a great question. The accuracy was a little bit worse for some of them. It was actually a little bit better for some of them. I think on balance, the accuracy did end up being worse. Like, it wasn't finding as accurate expressions as it otherwise would have, because the eGraph kept getting like destructively rewritten. So I think that is an avenue to like look into, like why is the accuracy worse for some cases, but then why is it like better for some cases? So
just another question.
Yeah.
Do you like so do you make like all the rewrites in Herbie's like rule set destructive, or did you choose which rules to make destructive, or have you tried like doing an ablation study, like which rules being destructive would change Herbie like by how much?
Yeah, so far I've only really tried it with like every single rewrite being destructive. I've tried restricting to specific rewrites. I'll need to experiment with that a little bit more, because like, for example, some of Herbie's rewrite rules are just like associativity, commutativity. Some of them are a bit more like multiply by 0, where it actually results in a lower cost term. So, but so far it's mainly been like making every single rewrite destructive.
So when you were talking about destructive rewrites, you had a bunch of rules for like when you wouldn't destroy a term, and those were all about like the structural validity of the eGraph, right? Whether it's like still an eGraph at the end. What about looking at cost information? You can imagine doing an extraction and never removing the cheapest node from an E-class or something like that.
Yeah, no, that'd be a really cool avenue for further exploration. I don't have time to talk about that here, but like taking in more information about the eGraph, as I said, right, instead of just like thinking about the structure of the eGraph. Thinking about like, oh, like if I remove this term, does that actually like, does this term actually contribute that much to the eGraph? Is a question that like my implementation doesn't answer at all. So thinking about like how useful is this term, and then maybe like thinking about the cost of specific terms would be really useful. Because like the sort of intuition behind why you can remove E-nodes in E-class is that for associativity and commutativity, it will add like a ton of like slightly different orderings to the eGraph, but then like maybe once you optimize, you rewrite those down to like a more optimized term, you kind of don't need what you had before. But as it stands right now, my implementation is very simple and does not think about that at all. So.
Okay, let's thank the speaker one more time.